Hey guys, so today we're going to talk about a different definition of acids and bases. It turns out that the Arrhenius definition that we talked about last time doesn't fit all situations. So it's a good one. And if you remember, it's anytime something creates hydronium, it's an acid. Anytime something creates, hydronium is this guy. Anytime something is put in water and it creates hydronium, it's an acid. Anytime something is put into water and it dissolves and forms hydroxide, it's a base. So that's the Arrhenius definition. The Bronsted-Lowry definition is actually a bit broader, and so it encompasses a few more things that Arrhenius did not. So the definition depends on the transfer of an H plus ion, a proton, a hydrogen, right? Um, so a Bronsted-Lowry acid is anything that donates an H plus. So for example, if I have HCl plus H2O, and that's going to produce H3O plus Cl minus. And this, by the way, is actually the very first example I gave you of an Arrhenius acid, because the HCl, hydrochloric acid, is actually producing hydronium. So that's what makes it an Arrhenius acid, or an acid by the Arrhenius definition. But the other thing that it's doing, if you look at this reaction, is this little hydrogen right here is being attached to this water molecule. So if you think about water, water has a couple of lone pairs on it if we think about Lewis structures. And those lone pairs are very attractive to those positive H plus ions. And so what's happening is this little H right here is attaching itself and forming a bond with one of these lone pairs, and that's what's creating our hydronium. So Bronsted and Lowry said an acid is anything that donates a proton, um, an H plus ion. And the thing about it, the thing that makes it a little bit better than the Arrhenius definition, is that it doesn't have to be with water. So for example, if I take the same HCl and I want to react it with, let's say, a negative ion, let's just say we're talking about, let's say we're talking about HSO4 minus. That's a polyatomic ion. Don't really have to worry about knowing what that is. It's a hydrogen sulfate ion. But if you notice that this is happening, or if you're a chemist and you're seeing this happening in the lab, and you're like, okay, well, there's no water, so there's no hydronium, so this can't be an acid. But you know it's an acid, because HCl is an acid. And what's actually happening here is that H is going to be transferred over to the HSO4 minus. And so it's going to end up giving you H2SO4 and Cl minus. So according to the Arrhenius definition, in this second reaction, HCl would not be an acid because there's no hydronium. Arrhenius was only concerned with things that created hydronium. But Bronsted and Lowry kind of said, well, wait a minute. Really what's happening is a proton, an H plus, is being donated from one thing to another. And so if you look at this second reaction, that's what's happening. Instead of giving an H to water, it's just giving an H to this negative ion and creating something new. So by the Bronsted-Lowry definition, HCl would be an acid in either case. In the Arrhenius definition, Arrhenius would look at this second reaction and say, well, I don't really know what's happening here because there's no hydronium being created. Okay, another one, or I'm sorry, the other thing that we have to look at here is Bronsted-Lowry bases. In Arrhenius bases, they always contained hydroxide, right? Like you always had like sodium hydroxide, potassium hydroxide, calcium hydroxide. Well, Bronsted-Lowry realized that not everything that acts like a base has hydroxide in it. So for example, if you look at window cleaner, like Windex, it contains NH3, ammonia. And that ammonia is a base. And so Bronsted-Lowry kind of looked at this molecule and figured, this stuff is acting as a base. it turns pH indicators like darker colors like blue and green, which indicates that it's basic. But it doesn't have hydroxide in it. So, we got to change the definition. Well, if you look at the flip of the acid definition, an acid is anything that donates a proton, an H+. Well, a base could be anything that accepts it. So, for example, if I took this NH3 and I reacted it with, let's say, HBr, that'd be hydrobromic acid. What's going to happen here in this reaction is the H from the HBr is going to be given to the NH3 and is going to make NH4 with a +1 charge, and it's going to leave behind the bromide ion, Br-. Okay, so the NH3, the ammonia, is acting as a base, because a base, according to Bronsted-Lowry, is anything that accepts a proton. So it's taking an H from the HBr, and it's forming this NH4+, and it's leaving, instead of HBr, now you've got Br-. And by the way, you don't have to be able to predict what's going to happen in these reactions. We're not going to quite get that far. I just want you to, if you see the full reaction, I want you to be able to recognize what is acting as a Bronsted-Lowry acid and what is acting as a Bronsted-Lowry base. Okay, so for that, let's take a look at Bronsted-Lowry reactions. And this actually was in a section in the CK12 reading that I didn't have you do as an assignment. If you want to go there, I will put the link in this Edpuzzle, possibly on Classroom too, so that you can read up on this before you finish up this part. But I'm going to explain everything pretty much here. Okay, so a Bronsted-Lowry acid-base reaction basically just means that a proton is transferred. And of course, proton is H+. So anytime we have a Bronsted-Lowry acid, it gives up a proton. Anytime we have a Bronsted-Lowry base, it accepts a proton. So if we have a Bronsted-Lowry acid-base reaction, that's a proton transfer reaction. So what I want you to do now is take a look at this first example and see if you can figure out which one is acting as a base on the left side here. So we have NH3 and H2O, and which one is acting as a Bronsted-Lowry base, remembering that a base is a thing that accepts a hydrogen. Okay, so you should have said that the NH3 on the left side over here is acting as a base. And the reason that you should say that is because if you look at what's happening to it, it's gaining an H+ ion as it moves from the left side to the right side. So you see over here it's NH3, over here it's NH4+, so it must have accepted a proton, which makes it a base. In the same reaction, we have something acting as an acid on the same side of the equation. And that would actually be water, which sounds kind of strange because water, we probably all know, is neutral. It's not acid or base. And the thing about water is it actually can act as an acid or a base depending on what it's with. So in this case, it's with NH3, which tends to act as a base and accept a hydrogen, which means that water, because of what it's with, because it's with a base, is going to act as an acid. Now, the interesting thing about these Bronsted-Lowry acid-base reactions is they tend to work in both directions. And so you can see that the arrow is going to the right, and we've got another arrow going to the left. And so what that means is, once you form the two products, those products can then collide and go back in the other direction. So if I look on the right side of the equation, I should have another proton transfer about to happen, shifting the reaction in reverse. So if you look at the NH4+ and the OH-, they're going to react to go back in this direction and give us NH3 and H2O. So you should be able to tell this, I think, but the NH4+ because it's going back to just having 3 H's, that means it must be the one that's giving up an H, giving up a proton. And so that means that for the reverse reaction, NH4 plus is acting as an acid. And OH minus, which, by the way, is that very important ion that we find in bases according to Arrhenius, is of course acting as a base because it would have to accept a hydrogen to become water. Okay, so let's do the same thing for this next reaction. See if you can identify the acid and base on the left-hand side of the equation, again, based on what they're becoming as we move to the right. So look for which of these two substances, the HSO4 minus and the water, which one is donating a proton and which one is accepting a proton, and that will tell you which one is acid and which one is base. Okay, so you should have said, in this case, that the HSO4 minus is acting as an acid because it is donating a hydrogen, a proton, to become SO4 2 minus, as we look at the right-hand side of the equation. Whereas water is acting as a base. Okay, and I want you to notice here that it's doing the exact opposite that it did in the previous equation. So here water was acting as an acid, down here water is acting as a base. Water is what we call amphoteric. And that simply means it can gain or lose H+. So again, it kind of goes back to what I said earlier. It depends on what it's with. If it's with an acid, like HSO4 1 minus, it's going to act as a base. If it's with a base, like NH3, it's going to act as an acid. See if you can also, going back to this bottom equation, see if you can also identify the acid and base on the right side. So H3O plus, SO4 2 minus, which one is the acid and which one is the base? Okay, so you should have said that the hydronium, the H3O plus, is acting as an acid, and that the sulfate, the SO4 2 minus, is acting as a base. Because if you look at what they're becoming, the H3O plus is most closely related to the water on the other side of the equation, meaning that it's becoming water, but it's doing that by donating a proton, which makes it an acid. The sulfate, SO4 2 minus, is most closely related to H, SO4 1 minus. They only differ by an H plus ion. So in order to become that, it would have to accept a proton. Okay, the last little concept here, we have this word conjugate. So conjugate basically just means that in any acid-base reaction, any Bronsted-Lowry acid-base reaction, you're going to have two compounds on either, or you're going to have compounds on opposite sides of the arrow that only differ by an H plus. So, for example, HNO2 in this reaction is very closely related to NO2 1 minus on the other side of the equation, and they differ by an H plus. In other words, if I took HNO2 and I subtracted an H plus, I donated an H plus, I would get NO2 1 minus, okay, and vice versa. They only differ by an H plus. Therefore, these guys are conjugates of each other. So one of the things that I sometimes ask you to do is just connect the conjugates with an arrow. And then you can also say, okay, so which one is acting as an acid and which one is acting as a base? Because the conjugate of an acid will always be a base. And I'll show you what I mean. HNO2 is acting as an acid because it's donating a proton to become NO2 1 minus. So it's an acid. I'm just going to put an A for acid. Now, why does that automatically make NO2 1 minus a base? Well, if we look at the reverse reaction, to get back to HNO2, we would have to accept a proton, accept an H plus, which by definition makes that substance a base. So the conjugate of our acid, in this case HNO2, will be a base, NO2 1 minus. Now, the other thing to keep in mind is there's always two sets of conjugates in any Bronsted-Lowry acid-base reaction. Okay, so that means the other two substances are also acting as acid and base. There's a couple different ways to look at this. We know that the phosphate, the PO43 minus, must be acting as either acid or base. We also know that its conjugate, by process of elimination, must be this HPO42 minus on the other side, not just by process of elimination, but also because they differ by an H plus, right? Um, so we know they're conjugates of each other. So I'll go ahead and draw an arrow. Now, also by process of elimination, we can figure out which of these two guys are acid and which are base. Basically because on the same side of the equation, you have to have one of each. You have to have an acid and a base. And we already have an acid, HNO2, so this must be a base. The other way to figure it out is simply, if I look at what's happening here, the phosphate, the PO43 minus, is gaining or accepting a proton to become HPO42 minus. So anything that gains a proton has to be a base. And its conjugate has to be an acid. And we also know that it's an acid because if I look at what's happening in the reverse direction, well, it's donating a proton to become PO4 3 minus. Okay. So that is our discussion of Bronsted-Lowry acids and bases and conjugates. Hopefully you're able to recognize conjugate acids and bases, also able to recognize what a Bronsted-Lowry acid is in a reaction. Again, you'll never have to write or predict the products of a Bronsted-Lowry acid-base reaction, but if I give you the products and reactants, you should be able to recognize what's acting as an acid and what's acting as a base.